tremendous ash cloud roiling out toward the northwest, and I can only assume that that was coming off.
When you see a volcano, you think of something that is gigantic and extremely powerful. But exactly how strong is a volcano? Is it really that impressive? In this video, I will explore the many different energies that a volcano produces. Before we begin, you must first know that volcanic eruptions are measured on a scale known as the Volcanic Explosivity Index. This scale ranges from 0 to 9, 0 being the least destructive, known as a Hawaiian eruption, and 9 being the most, known as an ultraplinian. We will focus on a 5, known as a plinian. Examples of 5s are Mount St. Helens and Mount Vesuvius. The characteristics that determine a volcano's volcanic explosivity index are the plume height, which is the length of the smoke cloud that comes out of a volcano, which for a 5 is larger than 25 kilometers, and the volume of magma, which is for a 5 is roughly 1,000 meters cubed. For this experiment, we will use the characteristics of Mount St. Helens for the variables. Now, Mount St. Helens erupted with a landslide, and that caused a lot of the magma to flow onto one side of the volcano. But for the sake of the experiment, we will assume that the magma shot straight up, and that the magma chamber had a cylindrical shape. The makeup of magma differs between volcanoes. Since we're using Mount St. Helens, the makeup of the magma in this volcano is known as dacite. Dacite has a specific gravity of 2.63, and specific gravity is measured as the density of the object divided by the density of water, which is 1,000 kilograms per meters cubed. Using this, we find the density of the magma at Mount St. Helens is about 2,630 kilograms per meters cubed. Since mass is density times volume, and we know that the volume of magma in this volcano is 1,000 meters cubed, then the mass of the magma at Mount St. Helens would be roughly 2,630,000 kilograms. We know that the mass is equal to 2,630,000 kilograms. If the force of gravity is equal to mass times the gravitational acceleration of the Earth, then the gravitational force would be equal to 25,774,000 newtons. We also know that the change in momentum is equal to the average force times time. We can make the change in momentum just final momentum since the initial momentum is 0, and we will assume that the time it takes to get to this momentum is about half a second. Using this equation, we find that the final momentum of the magma is 12,883,000 kilograms meters per second. With our momentum and the mass of the object, we can find the velocity using momentum equals mass times velocity. Solving for velocity, we get 4.9 meters per second. With this, we can calculate kinetic energy. For the potential, we will assume it is 0, since when the magma is shot out from the volcano, more comes from the Earth to fill its place. So that would mean the center of mass would be around the surface of the Earth, making the height 0, and the equation would cancel out. Now we have the mass and velocity. We could solve for kinetic energy. We get a total of 31,573,150 joules. This may not look like it, but this is a very small amount of energy. It is equal to about 16 pounds of TNT exploding. But volcanoes are known to be very big and powerful. Then what makes up for the small amount of kinetic energy? What about the heat energy that the magma emits? How powerful is the heat of the volcano? The formula for heat energy is Q equals mCT, where Q is energy, M is mass, C is specific heat, and T is change in temperature. We have the mass, and a quick search on the statistics of Mount St. Helens will offer the volcano's magma's temperature and the specific heat, which is a measurement of how much energy a substance will gain by increasing the temperature of a certain mass of it. The specific heat of magma is 1,256.04 joules per kilogram Celsius, and the original temperature of the magma is about 700 degrees Celsius. Using the equation Q equals mCT, we get the heat energy emitted by the magma to be roughly 2 trillion joules, which is equal to about half a ton of TNT exploding. Oddly enough, most of the energy a volcano emits is from the heat energy. This goes against what I originally believed, which was that most of the energy would come from the kinetic energy. Having the equal amount of energy to 1,000 pounds of TNT is no simple feat, and it just goes to show how powerful volcanoes really are.